Hello, biologists. Today we're going to talk about nutrient cycles. First, let's talk about biogeochemical cycles. A biogeochemical cycle is the path that an element takes through a living organism, back into the abiotic environment, and then into a living organism and back. So if we look here, we have our giraffe. Our giraffe is eating some plants, so it is consuming those elements. The elements go into the giraffe. It uses some for making tissue and then digests the rest. It's going to excrete it and it's going to get into the soil where detritivores are going to decompose it. It's also going to eventually die itself, and then its body is going to be decomposed. The same is true for the plant. The plant will also die and its body will decompose, and all of the nutrients in the living organisms will get released back into the environment through decomposition and then will be reuptake by plants and other living organisms to start the cycle all over again. We're going to start with the water cycle. We also call the water cycle the hydrologic cycle. Only about 2.5% of water on Earth is fresh water, and of that, less than 1% is easy to access. We have a diagram showing this. Here we have all of our salt water in a pie chart, and then the 2.5%, if we were to break it down, most of it would be in glaciers and permanent snow cover. Some would be in groundwater, swamps, damp soil, and then a little tiny bit here, 0.3% would be in lakes and rivers. Our hydrologic cycle is continuous, but we do have a high residence time for water molecules. A residence time is how long a water molecule stays in a specific reservoir. So here we have our biospheric, that's less than a week. We have atmospheric, only 1.5 weeks. Rivers, 2 weeks. So this is a short turnaround before it's returned to the ocean. Our oceans and seas, the water stays in them for about 4,000 years. And then if you look at glaciers and permafrost, it can be 1,000 to 10,000 years that the water molecule is stuck in there before it's returned to the ocean to be used again. So it's like how long it sits in its reservoir is the residence time. So a lot of our water is really locked in and pretty much inaccessible. Here is our hydrologic cycle. Our major reservoir for water is going to be the ocean. So 97.5% of our water is in the ocean. The majority of evaporation occurs over the ocean. The majority of precipitation occurs over the ocean. Precipitation is rain. Some of these heavy clouds full of moisture will move onto land, and then we'll have rain over land. That's where we get our fresh water on land. Some will evaporate back up and rain back down, but some will run off right back into the ocean to the major reservoir, and some will percolate. Percolate means to drip through small holes. So your coffee maker percolates coffee or percolates water through coffee beans, giving you coffee. That's what percolation is. So water will percolate through the small pores in the soil and it'll get into the water table. We have open aquifers and we have closed aquifers. So those are harder to access. We often call aquifers water tables. This is underground wells of water. If you dig deep enough anywhere on Earth, you will find water. It just sometimes is really, really, really deep. Here's another visual of the water cycle. We have a verbal description of it, or I guess a written description of it for you to read. Here, this one's a little bit more complicated, showing all the different types of actions that can be done with water. But what's the main point? The main point is our oceans are the major reservoirs. In these diagrams with the little border on the outside, that kind of looks like a picture frame, and we're going to see several of these. I want you to be looking at the size of the arrows and the directions of the arrows to figure out what's going on in these complex diagrams. So this water cycle here, we see the major big arrow going out of the reservoir is going to be evaporation over the ocean. So that's the biggest loss of water from the main reservoir. From our evaporation, we can see the water is in the atmosphere. Some of it's going to rain, some of it's going to be snow. Some of it is going to get right into our water tables. It's going to percolate and infiltrate the ground. From the groundwater, it will slowly go back to the ocean. but it might seep out, it might be a spring, it might go into a lake. And so it's showing you all these different intermediates of the rain that falls. Some can be in streams, we can have little waterfalls, we can have fog drip, we can have surface runoff. We'll still have evaporation happening over the terrestrial areas too, but overall it will slowly make its way back. So see all these arrows are headed back into our main reservoir of open oceans. Then we get into our nitrogen cycle. So the nitrogen cycle, our biggest reservoir is going to be the atmosphere. We're going to store nitrogen as N2, so nitrogen gas, and this is an inorganic molecule. It's not really available to anyone. You can see the big arrows in these diagrams are denitrification by bacteria, so that's how it's being released, and also fertilizers. That's how it's getting back into our reservoir. Note that there's only one arrow out. So to get it out, we have to follow this path down, and this is nitrogen-fixing bacteria. So nitrogen-fixing bacteria are key. They are so important to life on Earth, and that's because they can take this inorganic nitrogen gas and turn it into an organic molecule that plants and other organisms can use. So once you get it out of the atmosphere by nitrification-fixing bacteria, then it can be in your terrestrial system. It can go through plants and the animals that live here. We're having a lot of bacterial activity. We can also get it into our aquatic system from runoff from fertilizers and marine food webs, and then it will be reused by these bacteria that exist in the ocean as well. Eventually, both of those will release it up into the atmosphere, our major reservoir. We have large scale and small scale of nitrogen cycle as well. So in these diagrams, we're still looking at the thickness of the arrows as an indicator of volume, but now we have two different color arrows. We have purple, which are natural systems, and we have black, which are human-made systems. Our major atmospheric reservoir of nitrogen is here. To get it out, we're going to need those nitrogen-fixing bacteria. Here we have an aquatic reservoir. That aquatic reservoir is going to allow us to be used in terrestrial systems here, and that is also done by nitrogen-fixing bacteria. We can also get it out of the atmosphere of lightning, but note that's a very small amount. It's a tiny little arrow, and we do quantify it with these numbers here. But still, nitrogen-fixing bacteria, that's the key for both of these systems. For human systems, we have industrial fertilizer producer that's pulling some nitrogen out, and we're also using nitrogen-fixing bacteria in our crops. So we're counting agriculture as a human system in this diagram. Both of these systems are going to lead to a soil reservoir. It's not nearly as big as the atmospheric reservoir, but this is where it can be utilized by life. And while it's utilized by life, it will then be re-emitted into the atmosphere by bacteria. Now we have our small scale. So here's our small scale nitrogen cycle. All of this is happening in the bacteria, which love legumes. Legumes are a type of plant. Legumes include things like peas and soybeans and lentils. So legumes are awesome. If you garden, if you plant legumes, you're going to increase the nitrogen in your soil, which is really beneficial for your plants. So definitely plant some beans and some peas this year. Those nitrogen-fixing bacteria in the legumes create these little nodules, and this is filled with bacteria. So the plant creates a house for the bacteria, and in exchange, the bacteria pulls nitrogen out of the atmosphere and turns it into something the plants can use. What does it turn it into? It turns it into all of these different types of compounds that contain nitrogen that other organisms can then access because they are organic. That's the fixing part, is turning it from inorganic nitrogen gas into an organic containing hydrogen or oxygen that can be beneficial to other organisms. So we need those little bacteria to pull it out of the atmosphere, and then eventually little bacteria will release it back into the atmosphere. Next, we have our sulfur cycle. The sulfur cycle is interesting. We have our atmospheric reservoir, which is the air, and then it's going to get dissolved into the water that's up in these clouds. And the only way out, look, is precipitation, also called fallout. And it's going to drop down to our terrestrial system. If it falls over the ocean, it'll be the aquatic system. It's going to run off to the ocean. It'll be used by the marine organisms. It's then going to drop down and it's going to decomposition, which means it goes into the soil for a bit. And then volcanic activity will release it again into the atmosphere. We are also releasing sulfur. So we are adding to the system here. Then we have our phosphorus cycle. Phosphorus cycle again focus on volcanoes. Note that's the only way that it's coming out is aerosolized in volcano gases. Then it's going to drop down and it's going to become part of the terrestrial food web. It'll get dissolved into the soil. It'll become part of the rocks. We also use phosphorus in our fertilizers, and so it will run off from our agriculture into our ocean. And from the ocean, it will be used in our marine food systems and then eventually decompose and just like drop down as sediment. Then we have our carbon cycle. So the carbon cycle is probably the most dramatic one. The carbon cycle, we have our main reservoir, which is going to be the ocean. So this one is showing a lot of arrows that are the same size, but our ocean is a huge reservoir of carbon dioxide. We also have carbon dioxide in the air, but from the air, it's going to dissolve right into the oceans. So carbon dioxide dissolves into the oceans. This is our main reservoir. We're going to use it for photosynthesis. We're going to use it for cellular respiration. These two arrows, I think, should be swapped because photosynthesis is going to do the carbon fixing and respiration is going to do the carbon releasing as carbon dioxide. There's always a little bit of errors that we can find in images, so that's always fun. Either way, we're going to relay carbon from our oceans to the air. How do we get it into our air and into our oceans? Well, everything that does cellular respiration is going to release carbon dioxide. Organisms that do photosynthesis are going to pull it out of the air, and then humans' emissions are going to release it into the air. We also have a ton of microbes releasing it into the air, and we get it from volcanic activity. Historically, before humans were doing burning of fossil fuels, this is the main way that we got extra carbon into our atmosphere. And there were times when historically volcanic activity created huge jumps of carbon dioxide. It's also going to drip down into our soil, and it can get fossilized as fossil fuels or fossilized carbon. So this is a nice overview, but I like this one better. Here we get to see our main reservoir of carbon dioxide. It's in the ocean, so this is where we're storing most of our carbon dioxide. Carbon dioxide dissolves readily from the air into water. As it does, it creates carbonic acid, which we're going to talk about in just a second. But here, a small important reservoir of carbon dioxide. How does it get into the air? Well, it gets in there from respiration. Everyone that has a mitochondria is producing carbon dioxide. How does it get out of the air? By dissolving into the water or by photosynthesis. Those photosynthetic organisms are also doing respiration. Then we have long-term sediment and burial as fossil fuels. Note on these graphs, we have red arrows. These are natural cycles, and we have black arrows. These are human cycles. So humans are also contributing fossil fuel to the atmospheric reservoir. We do that by land use and by burning fossil fuels. And once it gets into the atmospheric reservoir, it dissolves into the ocean. So it's really being stored in the ocean. That's our major spot for it. We've got some great data that we're going to talk about in detail later in the term when we talk about climate change. But just a little preview for you. The carbon cycle has shifted when humans started burning fossil fuels. So we have graph A, carbon emissions from burning fossil fuels. And then we have global changes in atmospheric carbon dioxide over time. That's graph B. On this axis, we have carbon. So from 0 to 10,000. And then we have year 1400 to 2000. The same year span on this graph, but now we have carbon dioxide concentration. So carbon emissions in the atmosphere. And we can see that when we weren't burning fossil fuels, there wasn't a lot of carbon emissions, which makes total sense because we weren't doing it. Then the Industrial Revolution hit and we went wild and we really increased the amount of carbon emissions that we were releasing. Did it affect the atmosphere? Let's see. In this graph, we have a pretty consistent line up until the Industrial Revolution. And then like 1850, as we increased our carbon emissions, we also see that the carbon dioxide in the atmosphere jumped as well. So it seems like a really good correlation there, but don't worry, we're going to get into it in detail later in the term. I mentioned the carbonic acid that's created by carbon dioxide dissolving into water. I have a video for you about it. This is a process called ocean acidification, and this video focuses on the Oregon coast. So it's really fabulous. I'm excited for you to watch it. And to end our lecture, we're going to have three practice questions, and then we're going to talk about a diagram. So here's the first one. What is the largest reservoir of nitrogen? It is A, atmospheric nitrogen. Which of the following will have the highest level of biomagnified chemicals? You're going for your highest trophic level because it increases as you go up your trophic cascade. That's going to be your bluefin tuna. Why are nitrogen fixing bacteria important? We know fixing means taking an inorganic and making an organic. So that's what our goal is. Where's our reservoir? Atmospheric nitrogen. So that is going to be our answer. It's going to be C. And then here's our diagram. Take a moment, look at this diagram. We've done this before with bar graphs and with line graphs, but this is our first time doing it with a pie chart. So what is the independent variable? What is the dependent variable? Pause the video because I'm about to talk about it and I want you to have time to think about it. So the independent variable is the thing that you are changing as the experimenter, and the dependent variable is the thing that you are measuring. So in this case, the thing that we are changing is the type of greenhouse gas emission. That's what we're going to be looking at. And the thing that we are measuring is the percentages. So these items here, carbon dioxide from forestry, carbon dioxide from fossil fuels, methane, nitrous oxygen, fluorinated gases, those are the dependent variables. And the global greenhouse gases is our independent variable. I hope that was fun. Email me anytime with questions and we will talk soon. Bye.